Hey there, how was your day? Wherever you are in the world, whatever time it is, I'm glad you're here. Tonight, we're going to drift into the depths of our planet's greatest mystery. A mystery so vast, so quietly profound, that it covers more than 70% of Earth's surface, yet remains almost entirely unknown to us. What if I told you that we know more about the surface of Mars than we do about the bottom of our own oceans? That we've mapped less than 20% of the seafloor in detail, that entire mountain ranges, valleys deeper than the Grand Canyon, and ecosystems more alien than anything in science fiction exist just beneath the waves, waiting in darkness we've barely begun to penetrate. The ocean isn't just water. It's a three-dimensional universe of liquid space, stretching down into abyssal depths where the pressure would crush a human body in milliseconds, where no sunlight has ever touched, where creatures exist that seem to have evolved on a completely different planet. We're talking about a realm so foreign, so unexplored, that every deep-sea expedition still discovers new species, new geological formations, new mysteries that rewrite our understanding of life itself. If you find comfort in these gentle explorations of our planet's hidden wonders, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious minds like us, who find peace in contemplating the vast unknowns that surround us. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift down through layers of water into the deepest places on Earth. I'd love to know where you're listening from tonight. Are you near the ocean? Can you hear waves in the distance? Or perhaps you're far inland, surrounded by mountains and forests. There's something beautifully humbling about discussing the ocean's mysteries while we're all scattered across different corners of the world, each of us above sea level, looking down at a watery realm that remains largely as mysterious as it was to our earliest ancestors. Welcome to this journey into Earth's final frontier. Not the stars above, but the depths below. Tonight, we'll explore why 90% of our ocean remains a complete mystery and what that means for our understanding of our own planet. We'll descend through layers of water that few humans have ever seen, into realms where the rules of life as we know it bend and break in extraordinary ways. You're standing at the edge of the ocean on a calm, clear day. The surface stretches to the horizon, sparkling in sunlight, seemingly peaceful and familiar. Waves lap gently at your feet. The water looks inviting, approachable, almost domestic. But what you're seeing is just the thinnest skin of something unimaginably vast and alien. Beneath that placid surface lies a world more foreign than any distant planet we've observed through our most powerful telescopes. If you could drain all the water from the ocean, you'd reveal a landscape more dramatic and varied than any continent. Mountain ranges that dwarf the Himalayas. Canyons that make the Grand Canyon look like a small creek bed. Volcanic fields stretching for thousands of miles. Plains of sediment accumulated over millions of years, and trenches so deep that if you dropped Mount Everest into them, its peak would still be more than a mile underwater. This is the reality of our ocean. It's not just a body of water. It's an entire three-dimensional universe of liquid space, layered with different temperatures, pressures, and chemical compositions. It's a place where the familiar physics of our surface world transforms into something altogether more mysterious. Consider the sheer volume we're talking about. The ocean contains more than 99% of all livable space on our planet. While we terrestrial creatures fight for territory on the relatively tiny surface area of land, there's an entire civilization of life forms inhabiting a realm that extends not just horizontally across most of Earth's surface, but vertically through miles of water column. We're talking about a habitat with depth, with layers upon layers of different environments stacked on top of each other like floors in the universe's largest skyscraper. Yet despite this ocean covering more than 70% of our planet's surface, despite it containing the vast majority of Earth's livable space, we've explored less than 5% of it. Let that sink in for a moment. We've physically visited and studied less than 5% of the largest habitat on our own planet. It's as if we lived our entire lives in a massive mansion, but had only ever opened the door to peek into 1 or 2 rooms. The numbers become even more staggering when you consider the details. We've mapped the surface of the moon in greater detail than we've mapped our own ocean floor. We have more comprehensive charts of Mars than we do of the deepest parts of our seas. Our most detailed maps of the ocean floor have a resolution of about 5 kilometers, which means we're missing features smaller than 5 kilometers across. On land, that would be like having maps that couldn't show you anything smaller than a major city. But why is the ocean so difficult to explore? Why, in an age where we can land rovers on Mars and peer into the furthest reaches of the universe with space telescopes, do we still know so little about the waters that surround us? The answer lies in the fundamental hostility of the deep ocean to human exploration. Space, for all its dangers, is in many ways easier to explore than the deep sea. In space, you're dealing with a vacuum, radiation, and extreme temperatures. Challenging, certainly, but the engineering problems are relatively straightforward. You need to maintain pressure, provide life support, and protect against radiation and debris. The deep ocean presents a completely different set of challenges. As you descend, the pressure increases relentlessly. At sea level, we experience 1 atmosphere of pressure, about 14.7 pounds per square inch. That's the weight of the entire atmosphere pressing down on us, but our bodies are adapted to it. We don't even notice it. But in the ocean, pressure increases by 1 atmosphere for every 10 meters you descend. At 100 meters down, you're experiencing 10 times the pressure we feel at sea level. At 1,000 meters, it's 100 times greater. And the ocean's average depth is about 4,000 meters, where the pressure is 400 times what we experience on the surface. To put this in perspective, imagine the weight of 50 jumbo jets pressing down on every square meter. That's the pressure at the ocean's average depth. At the deepest parts of the ocean, in places like the Mariana Trench, the pressure exceeds 1,000 times what we experience at sea level. It's like having the weight of 50 elephants pressing down on every square inch of your body. This pressure would instantly crush any air-filled space. Human lungs would collapse in microseconds. The pressure is so immense that it changes the fundamental properties of water itself. At these depths, water becomes denser, more viscous. It behaves differently than the water we know at the surface. But pressure is just the beginning of the challenges. The deep ocean is also perpetually dark. Sunlight penetrates seawater, but only to a limited depth. In the clearest oceanic waters, sunlight can reach down to about 200 meters, but that's still less than 5% of the ocean's average depth. Below that, it's not just dark. It's a darkness more complete than anything most of us have ever experienced. It's the darkness of deep space, but filled with water under crushing pressure. This darkness means that photosynthesis, the process that powers most life on Earth's surface, is impossible in the vast majority of the ocean. The deep sea operates on completely different principles. Life down there has had to evolve entirely different strategies for survival, creating ecosystems that seem almost alien when compared to the familiar patterns of life we see on land or in shallow waters. The cold is another factor. While surface waters can be warm and inviting, the deep ocean is perpetually cold. Below about 1,000 meters, temperatures hover just above freezing, typically between 2 and 4 degrees Celsius. This isn't the pleasant coolness of a swimming pool. This is the kind of bone-deep cold that would kill a human in minutes, even with the best thermal protection. And then there's the simple challenge of distance. The deep ocean isn't just deep, it's also remote. To reach the deepest parts of the ocean, you need to travel not just down through miles of water, but often hundreds or thousands of miles from the nearest land. You're operating in one of the most isolated environments on Earth, where rescue or resupply is extremely difficult or impossible. These challenges mean that exploring the deep ocean requires technology that's in many ways more sophisticated than what we use for space exploration. A deep-sea submersible must withstand pressures that would crush a spacecraft like a tin can. It must operate in an environment where radio communication is impossible, where GPS doesn't work, where you're essentially flying blind through an alien landscape. The cost of deep ocean exploration reflects these challenges. A single dive to the deepest parts of the ocean can cost hundreds of thousands of dollars. The specialized equipment required is extraordinarily expensive to build and maintain. The ships needed to support deep-sea operations are massive, complex vessels that cost tens of thousands of dollars per day to operate. Compare this to space exploration, where once you've achieved orbit, you can operate for months or years with relatively little ongoing support. A deep-sea expedition requires constant, expensive surface support. Every dive is a major logistical undertaking. But perhaps the most significant challenge is simply the vastness of what we're trying to explore. The ocean covers more than 360 million square kilometers. To put that in perspective, if you could walk across the entire ocean floor at a steady pace, never stopping to rest, it would take you more than 4,000 years to cover it all. And that's just the floor. The ocean is three-dimensional. We're not just talking about exploring a surface, but an entire volume of space that contains more than 1.3 billion cubic kilometers of water. Given these immense challenges, it's perhaps not surprising that we've explored so little of our ocean. What is surprising is how much we've managed to discover in the small fraction we have explored. Every deep-sea expedition returns with discoveries that reshape our understanding of life, geology, and the history of our planet. In the brief glimpses we've had into the deep ocean, we've discovered entire ecosystems that operate without sunlight, creatures that seem to violate the basic rules of biology as we understand them, geological processes that dwarf anything happening on land, and evidence of Earth's history preserved in ways we never imagined possible. We've found underwater rivers and waterfalls, mountains taller than anything on land, and valleys deeper than any terrestrial canyon. We've discovered that the ocean floor is not a static, unchanging place, but a dynamic environment where new crust is constantly being created and destroyed, where massive geological forces reshape the landscape on scales that make human civilization seem like a brief flicker, and we've barely scratched the surface. Every new technology that allows us to probe deeper, to stay down longer, to see more clearly, reveals new mysteries. The more we learn about the ocean, the more we realize how much we don't know. This is why 90% of our ocean remains a complete mystery. Not because we lack the curiosity or the determination to explore it, but because we're dealing with an environment so vast, so hostile, and so alien that it challenges the very limits of human technology and ingenuity. But this mystery isn't just an academic curiosity. The ocean doesn't exist in isolation from the rest of our planet. It drives our weather, regulates our climate, and supports ecosystems that we're only beginning to understand. The ocean is intimately connected to every aspect of life on Earth, including our own survival. As we continue our journey into these depths, we'll discover that the ocean's mysteries aren't just about what's down there. They're about understanding our own planet, our own climate, and our own future. The ocean holds secrets that could reshape our understanding of life itself, secrets that could help us address some of the greatest challenges facing humanity. So as you settle deeper into this exploration, remember that we're not just talking about a distant, alien world. We're talking about the largest part of our own planet, a realm that's as much a part of Earth as the ground beneath your feet or the air you breathe. The ocean's mysteries are our mysteries, and understanding them is essential to understanding ourselves and our place in the cosmos. Tonight, as we drift deeper into this liquid cosmos, we encounter something that fundamentally challenges our understanding of what it means to explore. You see, when we think of exploration, we imagine maps being filled in, blank spaces disappearing, frontiers being conquered piece by piece. But the ocean doesn't cooperate with this familiar narrative of discovery. Instead, the ocean reveals itself in fragments, in brief glimpses, in tantalizing hints that only deepen the mystery. Every expedition that descends into the abyss brings back more questions than answers. Every new discovery opens doors to entire realms of possibility we never knew existed. It's as if we're trying to understand a vast library by reading only scattered sentences from random pages, attempting to piece together the story of our planet from incomplete chapters written in an alien language. Consider what happened in 1977, when scientists first discovered hydrothermal vents on the ocean floor. These weren't just geological features. They were entire ecosystems thriving in conditions that should have been impossible for life as we understood it. Here, in the crushing darkness of the deep sea, communities of creatures had evolved around underwater geysers that spewed superheated, mineral-rich water from the Earth's core. The water emerging from these vents reaches temperatures of over 400 degrees Celsius, hot enough to melt lead. Yet somehow, life not only survives in this environment, it flourishes. Giant tube worms, some reaching lengths of 8 feet, cluster around these thermal oases. They have no mouths, no stomachs, no digestive systems as we understand them. Instead, they host colonies of bacteria within their bodies, bacteria that can convert the toxic chemicals spewing from the vents into energy. This discovery didn't just add a new chapter to our understanding of ocean life. It rewrote the fundamental rules of biology. Before the discovery of hydrothermal vents, we believed that all life on Earth ultimately depended on energy from the sun. Plants capture sunlight through photosynthesis. Herbivores eat plants, carnivores eat herbivores, and so on. The sun was the engine that drove all life. But these deep-sea ecosystems operate on an entirely different principle. They derive their energy not from sunlight, but from chemosynthesis, the process of converting chemical energy into biological energy. These communities exist in complete independence from the sun, thriving in conditions that would be instantly lethal to most surface life. The implications of this discovery rippled far beyond marine biology. If life could evolve and thrive in such extreme conditions on Earth, what did that mean for the possibility of life elsewhere in the universe? Suddenly, places like Europa, Jupiter's ice-covered moon, or Enceladus, Saturn's frozen satellite, both of which are thought to harbor vast oceans beneath their icy shells, seemed like potential havens for life. But here's what makes this discovery even more remarkable. Hydrothermal vents were found purely by accident. Scientists weren't looking for new forms of life. They were studying the geology of the ocean floor, trying to understand how new oceanic crust is formed. The discovery of these thriving ecosystems was a complete surprise, a revelation that emerged from the darkness without warning. And this pattern repeats again and again in ocean exploration. We set out to study one thing and discover something entirely different, something that changes our understanding of what's possible. It's as if the ocean deliberately guards its secrets, revealing them only to those who approach with genuine curiosity rather than predetermined expectations. In the decades since that first hydrothermal vent discovery, we found that these oases of life are far more common than we initially thought. They exist along mid-ocean ridges, in back-arc basins, in places where tectonic plates meet and the Earth's interior meets the sea. Each new vent field we discover hosts its own unique community of creatures, many of which exist nowhere else on Earth. Some of these creatures seem to defy the basic principles of physics and chemistry. We've found bacteria that can survive in temperatures that would boil most organic molecules. Fish that live under pressures that would liquefy their tissues if they were brought to the surface. Creatures that can go months or even years without food, surviving in a state of suspended animation until conditions improve. But perhaps most remarkably, we've discovered that these deep-sea ecosystems may represent some of the oldest forms of life on Earth. The conditions around hydrothermal vents, with their chemical energy sources and protection from surface catastrophes, may be similar to the environments where life first evolved billions of years ago. In studying these deep-sea communities, we may be looking at living fossils, creatures whose ancestors witnessed the birth of life itself. Yet for every hydrothermal vent we've discovered and studied, there are likely dozens more waiting in the darkness. The ocean floor is riddled with volcanic activity, with tectonic processes that create new vents, even as others fade away. Each of these represents a potential oasis of life, a unique ecosystem that has evolved in isolation for thousands or millions of years. And hydrothermal vents are just one type of deep-sea ecosystem. We've also discovered cold seeps, areas where methane and hydrogen sulfide leak from the seafloor, creating entirely different chemical environments that support their own unique communities. We've found whale falls, the carcasses of great whales that sink to the ocean floor and become the foundation for complex ecosystems that can persist for decades. Each of these discoveries reveals new principles of life, new ways that organisms can adapt to extreme conditions, new connections between geology and biology that we never imagined. But they also reveal how much we still don't know. For every ecosystem we've studied in detail, there are countless others waiting in the vast, unexplored regions of the deep sea. The challenge isn't just the technical difficulty of reaching these places, it's also the sheer scale of what we're trying to understand. The deep ocean isn't a single environment, it's a collection of thousands, perhaps millions of different micro-environments, each with its own unique conditions, its own evolutionary history, its own potential for harboring life forms we've never encountered. Consider the Mariana Trench, the deepest part of the world's oceans. This isn't just a deep hole in the ocean floor. It's a complex system of trenches, ridges, and underwater mountains that stretches for over 2,000 kilometers. Within this single trench system, there are dozens of different environments, from the relatively shallow slopes near the surface to the crushing depths of Challenger Deep, the deepest point known on Earth. Each depth zone in the trench has its own unique conditions. The pressure changes dramatically as you descend. The temperature varies depending on proximity to volcanic activity. The chemistry of the water shifts as different minerals dissolve and precipitate. And at each level, life has found ways to adapt and thrive. At the bottom of Challenger Deep, more than 11 kilometers below the surface, the pressure exceeds 1,000 times what we experience at sea level. The temperature hovers just above freezing. No sunlight has ever penetrated to these depths. Yet even here, in what seems like the most hostile environment on Earth, we've found life. Microbes thrive in the sediments at the bottom of the trench, processing organic matter that drifts down from the surface world like snow. Amphipods, small shrimp-like creatures, scuttle across the seafloor, somehow managing to maintain their body structure despite pressures that would crush most life forms instantly. Even fish have been spotted at depths that were once thought to be beyond the limits of vertebrate life. But our knowledge of even this most famous of deep-sea environments remains fragmentary. Humans have visited the bottom of Challenger Deep only a handful of times. The first visit was in 1960, when Don Walsh and Jacques Picard descended in the bathyscaphe Trieste. They spent only 20 minutes on the bottom, with limited visibility and primitive instruments. It wasn't until 2012 that filmmaker James Cameron made the next solo dive to the bottom of the trench, followed by additional expeditions using increasingly sophisticated technology. Yet despite these heroic efforts, we've spent less time exploring the deepest part of our own planet than astronauts have spent walking on the moon. And Challenger Deep represents just one small point in the vast three-dimensional space of the ocean. Even if we could somehow explore every square meter of the ocean floor, we would still be missing the vast majority of the ocean's volume. The water column itself, the space between the surface and the seafloor, contains its own layers of mystery. The ocean is stratified into distinct zones, each with its own characteristics and inhabitants. Near the surface, in the sunlit epipelagic zone, familiar marine life flourishes. This is the ocean most of us know from documentaries and aquarium visits, filled with fish, dolphins, whales, and the complex food webs that depend on photosynthesis. But as you descend beyond the reach of sunlight, you enter the mesopelagic zone, the twilight realm where the last traces of surface light fade into eternal darkness. This zone, extending from about 200 to 1,000 meters deep, is home to one of the largest migrations on Earth, though most of us have never heard of it. Every night, billions of creatures rise from the depths toward the surface to feed, then descend again before dawn. This daily vertical migration involves more biomass than any terrestrial migration, yet it happens in complete invisibility, hidden beneath the waves. The creatures involved range from tiny zooplankton to squid the size of school buses, all participating in a rhythm of movement that has persisted for millions of years. Below the mesopelagic lies the bathypelagic zone, the true deep sea, where temperatures drop to near freezing and pressure becomes crushing. Here, in perpetual darkness, creatures have evolved adaptations that seem like science fiction. Fish with transparent heads and tubular eyes that can rotate to look upward. Jellyfish that create their own light shows with bioluminescent displays more complex than any human fireworks. Squid with eyes the size of dinner plates, the better to capture the faintest traces of light in the eternal darkness. And deeper still lies the abyssopelagic zone, where the pressure becomes so intense that only the most specialized creatures can survive. Here, the ocean floor begins to influence the water above it, creating currents and chemical gradients that shape entirely unique ecosystems. Each of these zones contains mysteries we're only beginning to unravel. The creatures that inhabit them have evolved over millions of years in isolation, developing biological solutions to problems we're only now learning to identify. Their biochemistry, their behavior, their ecological relationships all represent potential keys to understanding not just marine life, but life itself. But studying these creatures presents challenges that go far beyond simply reaching their habitat. Many deep-sea organisms are so specialized for their high-pressure, low-temperature environment that they cannot survive being brought to the surface. Their bodies, adapted to crushing pressures, literally fall apart when exposed to the lower pressures near the surface. It's as if they're made of a different kind of matter, one that only exists under the extreme conditions of the deep sea. This means that much of our knowledge of deep sea life comes from brief glimpses captured by underwater cameras, or samples collected by remotely operated vehicles. We're studying these ecosystems through a keyhole, catching fragments of behavior and biology that hint at complex systems we can barely comprehend. The more we learn about the ocean's vertical structure, the more we realize that each zone is not just a different depth, but essentially a different world, with its own physical laws, its own biological principles, its own evolutionary history. We're not just exploring one ocean, but dozens of interconnected oceans stacked on top of each other, each as foreign and mysterious as any alien planet. And this vertical complexity is just the beginning of the ocean's secrets. Because beneath all these layers of water lies perhaps the most mysterious realm of all, the seafloor itself. This isn't just the bottom of the ocean, it's an entirely different planet, one that operates according to geological principles we're only beginning to understand. The seafloor is alive in ways that defy our surface-dwelling intuitions. It breathes, releasing plumes of superheated water and gas. It grows, as new oceanic crust is born at mid-ocean ridges and spreads outward like a slow-motion explosion. It dies, as old crust is consumed at subduction zones, pulled back into the Earth's molten interior to be recycled over millions of years. These processes create a landscape in constant motion, though the changes happen so slowly that they're invisible to human perception. Mountain ranges rise and fall, valleys open and close. Entire sections of seafloor drift across the planet like massive puzzle pieces, carrying with them the history of our planet, written in layers of sediment and rock. But here's what makes this geological drama even more extraordinary. We've mapped less than 20% of the seafloor in detail. The rest remains as mysterious as an undiscovered continent. We know more about the surface features of Mars, a planet nearly 40 million miles away at its closest approach, than we do about the bottom of our own oceans. The maps we do have of the ocean floor reveal a world of staggering geological diversity. The Mid-Atlantic Ridge, a mountain range that runs down the center of the Atlantic Ocean, is longer than the Andes, the Rockies, and the Himalayas combined. Yet most people have never heard of it because it lies hidden beneath miles of water. The Peru-Chile Trench stretches for over 5,000 kilometers along the western coast of South America, creating underwater canyons so deep that they make the Grand Canyon look like a shallow creek. The Mariana Trench, which we touched on earlier, plunges to depths that would swallow Mount Everest with room to spare. But these are just the features large enough to show up on our crude maps. The reality is that the seafloor contains countless smaller features that remain completely unknown. Underwater volcanoes that dwarf anything on land, coral reefs growing in the deep ocean, sustained not by sunlight, but by the chemical energy seeping from the Earth's interior. Fields of rocks and sediments that preserve the history of our planet's climate, its magnetic field, its collisions with asteroids and comets. Each of these features represents not just a geographical curiosity, but a potential window into Earth's past and future. The sediments accumulating on the ocean floor contain a record of our planet's history more detailed and complete than anything preserved on land. In these deep-sea archives, scientists can read the story of ancient climate changes, mass extinctions, the rise and fall of different forms of life over hundreds of millions of years. But accessing this historical record requires technology and techniques that push the boundaries of what's possible. Drilling into the ocean floor to extract sediment cores is like performing surgery while dangling from a rope several miles long in complete darkness, while the patient is constantly moving. The precision required is extraordinary, and the margin for error is essentially zero. When we do manage to extract these sediment cores, what we find often revolutionizes our understanding of Earth's history. We've discovered evidence of massive climate changes that happened far more rapidly than we previously thought possible. We've found traces of asteroid impacts that caused mass extinctions. We've uncovered evidence of ancient ice ages and warm periods that help us understand how our planet's climate system operates over geological timescales. But for every sediment core we've extracted, there are thousands of potential drilling sites that remain untouched. Each represents a different chapter in Earth's story, a different perspective on the events that shaped our planet. The ocean floor is essentially a vast library of Earth's history, and we've read perhaps one page out of every 1,000. The challenge of exploring the seafloor goes beyond just the technical difficulties of operating in such an extreme environment. It's also about scale and time. The processes that shape the ocean floor operate over timescales that dwarf human civilization. A single volcanic eruption on the seafloor might create new terrain that will persist for millions of years. The movement of tectonic plates reshapes entire ocean basins over tens of millions of years. Understanding these processes requires not just sophisticated technology, but also a fundamental shift in how we think about time and change. We're used to landscapes that seem permanent and unchanging within human lifespans. But the ocean floor teaches us that what seems solid and permanent is actually in constant flux, constantly being created and destroyed and recreated in an endless cycle that has been going on for billions of years. This geological perspective reveals something profound about our planet. Earth isn't a static ball of rock with some water on top. It's a dynamic, living system where the oceans, the atmosphere, and the solid Earth are all interconnected parts of a single, complex machine. The ocean doesn't just sit on top of the planet. It's an integral part of how the planet works, influencing everything from the weather we experience to the magnetic field that protects us from harmful cosmic radiation. But perhaps the most humbling aspect of our ignorance about the seafloor is what it reveals about the limitations of human perception. We're surface creatures, adapted to see and understand the thin shell of the planet where air meets land. Our entire evolutionary history has prepared us to navigate a world of mountains and valleys, forests and plains, rivers and lakes. The ocean floor represents a completely different kind of landscape, one that operates according to principles we're only beginning to grasp. It's a world where water pressure replaces air pressure, where chemical energy replaces solar energy, where the boundaries between living and non-living become blurred in ways that challenge our basic categories of understanding. Every time we manage to peer into this alien landscape, we discover phenomena that force us to expand our conception of what's possible. We find ecosystems that thrive in conditions that would be instantly lethal to surface life. We discover geological processes that dwarf anything happening on land. We uncover evidence of the planet's history that rewrites our understanding of how Earth became the world we know. Yet these discoveries represent just the tiniest fraction of what's waiting to be found. The vast majority of the seafloor remains as mysterious as it was to our earliest ancestors, who first gazed out at the ocean and wondered what lay beneath the waves. This mystery isn't just academic. The ocean floor contains resources that could be crucial to humanity's future. Rare earth elements essential for modern technology. Mineral deposits that could power new forms of clean energy. Biological compounds that could lead to breakthrough medicines. But accessing these resources requires understanding the ecosystems and geological processes that created them, knowledge that we're only beginning to acquire. The ocean floor also plays a crucial role in regulating Earth's climate. The deep ocean currents that circulate around the planet, carrying heat from the equator to the poles and cold water back again, are shaped by the topography of the seafloor. Changes in these circulation patterns, caused by geological processes we don't fully understand, could dramatically alter global climate patterns. As we continue our descent into the ocean's mysteries, we begin to understand that we're not just exploring a different part of our planet. We're exploring a different way of being, a different set of possibilities for what life and landscape can become. The ocean challenges every assumption we have about the nature of our world, revealing that the familiar surface environment we call home is just one small variation in a much larger theme. The seafloor teaches us humility. It reminds us that despite all our technological achievements, despite our ability to send spacecraft to other planets and peer into the furthest reaches of the universe, we still don't understand the planet beneath our feet. We're still strangers to the vast majority of our own world. But this mystery also offers hope. If the small fraction of the ocean we've explored has already revealed such extraordinary diversity and wonder, what marvels await us in the 90% that remains unknown? What forms of life might exist in the deepest trenches? What geological processes might be shaping landscapes we've never seen? What secrets of Earth's history lie buried in sediments we've never sampled? The ocean's mysteries aren't just about what's down there. They're about what's possible. They're about the incredible creativity of life and geology operating over scales of time and space that stretch human imagination to its limits. They're about recognizing that our planet is far stranger, far more wonderful, and far more complex than we ever dared to imagine. As you drift deeper into contemplation of these underwater realms, remember that every drop of water in every ocean was once part of this vast, interconnected system. The water you drink, the rain that falls, the clouds that drift overhead, all are part of the same hydrological cycle that connects the surface world to the deepest abyssal plains. You are not separate from these ocean mysteries. You are part of them. The calcium in your bones came from ancient marine organisms. The salt in your blood echoes the chemistry of primordial seas. The oxygen you breathe was partially produced by marine photosynthesis. In the most literal sense, you carry the ocean within you, just as the ocean carries the memory of every creature that has ever lived within its depths. The ocean's mysteries are humanity's mysteries. Understanding them isn't just about satisfying scientific curiosity. It's about understanding ourselves, our planet, and our place in the grand story of life on Earth. The 90% of the ocean that remains unexplored isn't just unknown territory. It's unknown possibility, waiting to reshape our understanding of what it means to be alive on this remarkable planet we call home. And so we arrive at perhaps the most profound realization of all. The ocean's mysteries aren't confined to the deep places we cannot reach. They exist in dimensions we're only beginning to perceive, in connections we're only starting to understand, in timescales that humble our brief human perspective on existence itself. Consider for a moment the invisible rivers that flow through the ocean. Not metaphorical rivers, but actual currents of water moving with the persistence and power of terrestrial rivers, yet flowing through liquid rather than carving through solid ground. These underwater rivers carry more water than all the rivers on land combined, yet they remain largely invisible to us, detectable only through subtle changes in temperature, salinity, and the movement of deep-sea creatures that follow their ancient paths. The Gulf Stream, that great river in the Atlantic, carries warm water northward, with a flow rate 150 times greater than the Amazon River. But the Gulf Stream is just one thread in a vast tapestry of ocean circulation that connects every body of water on Earth. Water that sinks in the North Atlantic might not surface again for 1,000 years, during which time it travels a path that circumnavigates the globe, carrying with it nutrients, heat, and chemical signatures from every ocean basin it passes through. This global circulation system, sometimes called the ocean's conveyor belt, is one of the most important climate regulators on our planet. Yet we understand its workings only in the broadest terms. We know that changes in this circulation have triggered ice ages and warm periods throughout Earth's history. We know that relatively small disruptions can cause massive shifts in global weather patterns. But the precise mechanisms, the feedback loops, the tipping points that could alter this system remain largely mysterious. Part of the challenge is that ocean circulation operates on timescales that dwarf human observation. The deep waters flowing through the ocean's depths began their journey at the surface decades or centuries ago. The chemical signatures they carry, the temperatures they maintain, the life forms they support, all reflect conditions that existed long before any human was there to observe them. Understanding ocean circulation isn't just about studying what's happening now. It's about deciphering a complex message written in water that has been traveling for longer than human civilization has existed. But the ocean's temporal mysteries extend far beyond circulation patterns. In the deepest parts of the sea, time itself seems to move differently. Creatures that would live for a few years in surface waters can survive for centuries in the deep ocean's cold, stable environment. We've found deep-sea corals that are thousands of years old, sponges that have been filtering seawater since before the Roman Empire, fish that may have been swimming in the same territories for decades or even centuries. These ancient creatures aren't just biological curiosities, they're living libraries, their bodies containing chemical records of ocean conditions stretching back through human history and beyond. The growth rings in deep-sea corals record changes in ocean temperature and chemistry with the precision of tree rings, but over much longer time periods. The shells of deep-sea organisms preserve isotopic signatures that tell us about ancient ocean conditions, about climate changes that occurred long before humans began keeping records. But accessing these biological archives requires finding creatures that live in some of the most remote and inaccessible places on Earth. A deep-sea coral that has been growing for 1,000 years might exist in a single location on a seamount thousands of miles from the nearest land, at depths where the pressure would crush conventional research equipment. Each sample we manage to collect represents a heroic effort of exploration and a precious glimpse into the ocean's long memory. The temporal dimension of ocean mysteries becomes even more complex when we consider the role of the deep sea in Earth's carbon cycle. The ocean absorbs enormous quantities of carbon dioxide from the atmosphere, storing it in various forms throughout the water column and in seafloor sediments. This process has been crucial in regulating Earth's climate over geological timescales, preventing our planet from experiencing the runaway greenhouse effect that turned Venus into a hellish, uninhabitable world. But the mechanisms by which the ocean stores and releases carbon are extraordinarily complex and remain poorly understood. Carbon can be stored in the ocean for anywhere from months to millions of years, depending on how it enters the system and where it ends up. Some carbon is quickly recycled as marine organisms consume and excrete it. Other carbon becomes incorporated into shells and skeletons that eventually sink to the seafloor, where it may remain buried for millions of years. The deep ocean acts as a vast carbon reservoir, containing far more carbon than the atmosphere and all terrestrial ecosystems combined. Changes in how this reservoir operates could dramatically alter global climate patterns. Yet our understanding of these processes is based on measurements from a tiny fraction of the ocean, observations that span only a few decades of the centuries or millennia, over which these systems naturally vary. This uncertainty becomes particularly troubling when we consider how human activities are already changing ocean chemistry. The carbon dioxide we're adding to the atmosphere isn't just warming the planet, it's also making the ocean more acidic, as seawater absorbs CO2 and forms carbonic acid. This ocean acidification is happening faster than at any time in the last 50 million years, creating conditions that many marine organisms have never experienced in their evolutionary history. But predicting how ocean ecosystems will respond to these changes requires understanding baselines we've never measured. What was the natural variability in ocean chemistry before human influence? How have marine ecosystems adapted to past changes in ocean conditions? What are the thresholds beyond which current systems might collapse or transform into something entirely different? These questions become even more complex when we consider the deep-sea ecosystems that depend on chemical energy rather than sunlight. These chemosynthetic communities around hydrothermal vents and cold seeps might be relatively isolated from surface changes, or they might be connected to global ocean systems in ways we don't yet understand. Changes in ocean circulation, temperature, or chemistry could affect the geological processes that create and maintain these unique habitats. The creatures living in these extreme environments represent some of the most ancient lineages of life on Earth. Their biochemistry, their metabolic pathways, their genetic codes all contain information about the early history of life that we're only beginning to decode. But many of these species are known from only a few specimens collected from single locations. We don't know how widespread they are, how their populations are structured, or how resilient they might be to environmental changes. The pharmaceutical potential of these deep-sea organisms is enormous. Creatures that have evolved to survive in extreme conditions often produce chemical compounds with remarkable properties. Deep-sea sponges have yielded compounds that show promise for treating cancer. Bacteria from hydrothermal vents have provided enzymes that are essential for modern molecular biology techniques. Organisms from the deep ocean have contributed to treatments for pain, inflammation, and infectious diseases. But this potential remains largely untapped because we've sampled such a tiny fraction of deep-sea biodiversity. Every new species we discover represents a potential breakthrough in medicine, biotechnology, or our understanding of the fundamental processes of life. Yet the cost and difficulty of deep-sea exploration means that most of these species remain unknown, their secrets locked away in the darkness of the abyss. The ocean's biological mysteries are compounded by its physical ones. We're still discovering new features of underwater geography on a regular basis. Seamounts, underwater mountains that rise from the ocean floor, are scattered throughout the world's oceans like islands in an invisible archipelago. Each seamount creates its own unique environment, its own patterns of currents and nutrients, its own isolated ecosystem that may have evolved in complete separation from similar habitats. We estimate that there may be more than 100,000 seamounts in the world's oceans, but we've studied only a few hundred in any detail. Each one we explore reveals new species, new ecological relationships, new insights into how life adapts to isolated island environments beneath the sea. But the vast majority remain unmapped, unexplored, their biological treasures unknown. The technology required to explore these underwater mountains pushes the boundaries of what's possible. Unlike terrestrial mountains, which can be studied using aircraft, satellites, and relatively straightforward ground-based exploration, seamounts must be approached through miles of water under crushing pressure. The equipment needed to map their topography, sample their ecosystems, and study their geological structure represents some of the most sophisticated technology humans have ever developed. Yet even our most advanced instruments provide only brief glimpses of these underwater worlds. A typical research expedition might spend weeks traveling to a remote seamount, then have only a few days of actual exploration time before weather, equipment limitations, or logistical constraints force a return to port. The data collected during these brief windows represents years of analysis and interpretation, but it can only hint at the complex ecosystems and geological processes operating on these isolated underwater peaks. The challenge becomes even greater when we consider the dynamic nature of the ocean environment. Unlike terrestrial ecosystems, which change relatively slowly in response to seasonal cycles and long-term climate trends, ocean ecosystems can shift rapidly in response to currents, temperature changes, and the movement of nutrients and organisms through the water column. A seamount that hosts a thriving coral reef during one season might be bathed in nutrient-poor water during another, causing dramatic changes in the abundance and diversity of life. The creatures living on these underwater mountains must be adapted not just to the extreme conditions of the deep sea, but also to rapid changes in their environment that would be impossible to predict without long-term monitoring. But long-term monitoring of deep-sea environments is extraordinarily difficult and expensive. Unlike weather stations on land, which can operate for years with minimal maintenance, instruments placed in the deep ocean must withstand crushing pressure, corrosive seawater, and complete isolation from any possibility of repair or adjustment. The batteries that power these instruments, the sensors that collect data, the communication systems that transmit information to the surface, all must be designed to operate flawlessly in one of the most hostile environments on Earth. Even when these technological challenges are overcome, the data collected raises new questions about the fundamental nature of ocean ecosystems. We're discovering that the boundaries between different marine environments are far more complex and dynamic than we previously understood. The deep sea isn't a single uniform habitat, but a complex mosaic of interconnected environments, each influencing the others in ways we're only beginning to appreciate. Creatures that spend part of their life cycle in the deep ocean and part in shallower waters create connections between different depth zones that we never suspected. Nutrients and organic matter cascade down from surface waters in patterns that change seasonally and geographically. Chemical signals produced by deep-sea organisms may influence the behavior of surface-dwelling species, creating feedback loops that span the entire water column. Understanding these connections requires a fundamental shift in how we think about ocean ecosystems. Instead of studying individual species or single locations, we need to understand the ocean as an integrated system where changes in one place can have cascading effects throughout the entire marine environment. But achieving this systematic understanding requires data from across the ocean's three-dimensional space and through timescales that span decades or centuries. The computational challenges of modeling such a complex system are staggering. Even with our most powerful supercomputers, we can only approximate the behavior of ocean systems over limited areas and time periods. The interactions between physical processes like currents and temperature, chemical processes like nutrient cycling and pH changes, and biological processes like predation and reproduction create a web of complexity that strains the limits of human understanding. Yet this complexity isn't just a scientific challenge, it's also a source of wonder and humility. Every new discovery in the ocean reveals new layers of complexity, new connections we never imagined, new forms of beauty and adaptation that expand our conception of what's possible in the natural world. The bioluminescence that illuminates the deep sea, creates light, shows more spectacular than any human fireworks display. Creatures produce light through chemical reactions that that are far more efficient than any artificial lighting technology we've developed. They use this light to communicate, to hunt, to defend themselves, and to navigate through the eternal darkness of the deep ocean in ways we're only beginning to understand. Some deep-sea organisms can produce multiple colors of light, creating complex patterns and displays that may represent a form of communication as sophisticated as any human language. Others can control the intensity and duration of their bioluminescence with precision that rivals the most advanced electronic displays. Still others coordinate their light production with other individuals, creating synchronized displays that can be seen across vast distances in the deep ocean's darkness. But studying bioluminescence in the deep sea presents unique challenges. The light-producing organs of these creatures are often fragile and sensitive, damaged by the pressure changes and handling required to bring specimens to the surface. The chemical reactions that produce bioluminescence may be disrupted by changes in temperature, pressure, or chemical environment. Many of the most spectacular displays occur only under specific conditions that are difficult to replicate in laboratory settings. This means that much of our knowledge of deep-sea bioluminescence comes from brief observations made during deep-sea dives, captured on video under challenging conditions with limited time for detailed study. We know that bioluminescence is widespread in the deep ocean, but we understand very little about how these systems evolved, how they're controlled, or what role they play in the complex social and ecological relationships of deep-sea communities. The ocean's acoustic environment presents another dimension of mystery that we're only beginning to explore. The deep sea isn't silent. It's filled with sounds produced by geological processes, by the movement of water, and by the creatures that inhabit these depths. But these sounds travel through water in ways that are fundamentally different from how sound moves through air, creating acoustic environments that have no equivalent in the terrestrial world. Some deep-sea creatures produce sounds that can travel for hundreds or even thousands of miles through the ocean's sound channel, a layer of water where sound waves can propagate with minimal loss of energy. These long-distance acoustic signals may be used for communication between individuals separated by vast distances, or for navigation across ocean basins, or for purposes we haven't yet imagined. But detecting and interpreting these sounds requires sophisticated hydrophone arrays and analysis techniques that can distinguish biological signals from the constant background noise of geological and oceanographic processes. The ocean is filled with sounds from breaking waves, shifting sediments, underwater landslides, volcanic activity, and the movement of water masses that create a complex acoustic landscape we're only beginning to map. Understanding the ocean's acoustic environment isn't just a matter of scientific curiosity. Human activities are adding new sources of noise to the ocean, from shipping traffic to offshore construction to military sonar systems. These anthropogenic sounds may be disrupting communication systems that marine organisms have relied on for millions of years, but we understand so little about natural ocean acoustics that we can barely assess the impact of these changes. The deep ocean's acoustic mysteries connect to larger questions about how marine ecosystems function and how they're being affected by human activities. But answering these questions requires long-term studies of ocean systems that span multiple decades and cover vast areas of the global ocean. Such studies demand levels of international cooperation, technological development, and sustained funding that push the boundaries of what human societies have ever attempted in scientific research. As we drift deeper into contemplation of these oceanic mysteries, we begin to understand that the ocean's unknowns aren't just gaps in scientific knowledge. They represent fundamental questions about the nature of life, the history of our planet, and our place in the cosmos. The ocean contains secrets that could reshape our understanding of evolution, climate, and the potential for life beyond Earth. But perhaps more importantly, the ocean's mysteries remind us of the limits of human knowledge and the importance of humility in the face of natural complexity. Despite all our technological achievements, despite our ability to peer into the furthest reaches of the universe and manipulate matter at the atomic level, we remain strangers to most of our own planet. This recognition isn't cause for despair, but for wonder. The ocean's vast unknowns represent infinite possibility, endless potential for discovery and understanding. Every expedition into the deep sea brings back new questions that reshape our conception of what's possible. Every new species discovered, every new ecosystem explored, every new geological process revealed adds another piece to the vast puzzle of Earth's complexity. The 90% of the ocean that remains unexplored isn't just unknown territory. It's a reservoir of mystery that ensures future generations will inherit a world still capable of surprising and inspiring them. In an age when it sometimes seems that all frontiers have been conquered, when satellite imagery and global positioning systems have mapped every corner of the land surface, the ocean remains truly wild, truly unknown, truly capable of humbling human presumption about our mastery of the natural world. As you settle deeper into this liquid meditation, remember that you are connected to these oceanic mysteries in ways both profound and intimate. The water cycle that sustains all terrestrial life begins and ends in the ocean. The oxygen you breathe was partially produced by marine photosynthesis. The climate that shapes your daily experience is regulated by ocean currents and chemical processes we're only beginning to understand. The ocean's mysteries aren't distant abstractions. They're part of the fundamental systems that make life on Earth possible. Understanding them isn't just about satisfying scientific curiosity, it's about understanding the planet we depend on for our survival, the complex systems that have sustained life for billions of years, and the delicate balances that we're only now learning to appreciate. Tonight, as you drift between waking and sleeping, between the familiar world of air and light, and the mysterious realm of water and darkness, remember that the ocean's secrets are still being written. Every tide that flows, every current that shifts, every creature that moves through the depths adds another line to the vast story of our planet's ongoing evolution. The 90% of the ocean that remains unexplored isn't just waiting for us to discover it. It's actively creating new mysteries, new forms of life, new geological processes that will surprise and challenge future explorers. The ocean isn't a museum of ancient wonders, but a living laboratory where the future of life on Earth is being written in currents and chemistry, in the endless dance of creatures adapting to an ever-changing world. In this vast liquid cosmos that covers most of our planet, in these depths that remain as mysterious as any distant galaxy, lies the reminder that wonder isn't something we've outgrown or conquered. It's something that surrounds us, something that flows beneath every coastline, something that connects every drop of rain to the vastest currents of planetary circulation. The ocean's mysteries are our inheritance and our challenge, our humbling and our inspiration. They remind us that despite all our knowledge, despite all our technology, we remain explorers on a planet that still holds infinite secrets, infinite possibilities for discovery and wonder. And yet, even as we contemplate these vast unknowns, there's something even more mysterious happening in the ocean's depths. Something that challenges not just our understanding of marine life, but our fundamental assumptions about the nature of existence itself. Deep beneath the waves, in trenches so remote that they might as well be on another planet, scientists have discovered ecosystems that seem to operate outside the normal rules of biology. These aren't just unusual adaptations to extreme conditions. They're entirely different approaches to being alive, alternative solutions to the problem of existence that evolution has crafted in the isolation of the abyss. Consider the glass sponge reefs of the deep Pacific. These structures, built by creatures that are more ancient than dinosaurs, create underwater cities that can stretch for miles. The sponges that build these reefs can live for thousands of years, growing so slowly that a structure the size of a building might represent centuries of patient construction. Their bodies are made of glass, literally silicon dioxide spun into intricate lattices that are stronger than many human-made materials. But here's what makes these reefs truly extraordinary. They exist in a state of suspension between life and death that defies our normal categories. The sponges that build them are alive, but barely. They have no nervous system, no digestive system as we understand it, no apparent way of sensing or responding to their environment. Yet somehow they coordinate their growth with other sponges across vast distances, creating structures of stunning beauty and complexity. These glass cities rise from the seafloor like underwater cathedrals, their spires and chambers providing habitat for countless other species. Fish swim through passages that took centuries to form. Crabs scuttle across bridges of living glass. Entire communities of smaller organisms make their homes in the intricate architecture of these ancient builders. But we've only recently discovered these reefs, and we understand almost nothing about how they function. How do the sponges communicate across such distances? How do they coordinate their growth to create such precise structures? How do they sense the presence of other sponges and respond to changes in their environment? The mechanisms that allow these simple creatures to create such complex architecture remain completely mysterious. And glass sponge reefs are just one example of the alternative forms of life that exist in the ocean's depths, in the crushing darkness of deep-sea trenches. We've found entire ecosystems based on principles that seem to contradict everything we thought we knew about the requirements for life. There are communities of organisms that derive their energy not from food in any conventional sense, but from the radioactive decay of elements in the seafloor sediments. Bacteria that can survive in environments so toxic that they would kill most other life forms instantly. Creatures that exist in a state of suspended animation for years at a time, awakening only when specific chemical conditions trigger their metabolism back into activity. Some of these organisms challenge our most basic assumptions about the nature of individual identity. In the deep ocean, the boundaries between one creature and another often become blurred in ways that make no sense from our surface-dwelling perspective. We've found organisms that exist as colonies of individuals so interconnected that it's impossible to say where one ends and another begins. Creatures that can merge and separate at will, sharing genetic material and metabolic processes in ways that create temporary superorganisms. These discoveries force us to reconsider what we mean when we talk about life itself. Are these deep-sea entities individual organisms, or are they something else entirely? Communities, processes, forms of existence for which we don't yet have adequate words or concepts. The implications extend far beyond marine biology. If life can take such radically different forms in the extreme environments of our own planet, what might be possible elsewhere in the universe? The conditions in the deep ocean, with their crushing pressures, extreme temperatures, and toxic chemistry, are actually similar to conditions that might exist on other worlds. The moons of Jupiter and Saturn, with their subsurface oceans, might harbor forms of life as alien and wonderful as anything we've found in our own depths. But studying these alternative forms of life presents challenges that go beyond the technical difficulties of deep-sea exploration. These organisms often exist on timescales that dwarf human observation. A single generation might last for decades or centuries. Changes in their communities might unfold over millennia. Understanding their life cycles, their ecological relationships, their evolutionary history requires patience and persistence on scales that test the limits of human scientific endeavor. Consider the deep-sea coral gardens that grow on seamounts in the darkest parts of the ocean. These aren't the colorful tropical corals we see in shallow water documentaries. They're ancient, slow-growing structures that can reach enormous sizes over thousands of years. Some individual coral colonies are older than human civilization, their growth rings recording changes in ocean conditions that span recorded history and beyond. But these deep-sea corals are incredibly fragile. They grow so slowly that damage from human activities like deep-sea fishing or mining can destroy structures that took millennia to form. A single pass of a fishing net can eliminate coral gardens that represent thousands of years of growth, erasing libraries of environmental history that can never be replaced. The loss of these ancient ecosystems isn't just an environmental tragedy. It's a loss of information about our planet's history that we're only beginning to learn how to read. Each coral colony, each glass sponge reef, each community of deep-sea organisms represents a unique archive of environmental conditions stretching back through time. When we destroy these structures, we're not just eliminating current biodiversity, we're erasing the records of our planet's past. But protecting these ecosystems requires understanding them first, and understanding them requires sustained observation over periods that challenge the normal timescales of scientific research. How do you study an organism that lives for thousands of years? How do you understand an ecosystem that changes so slowly that significant shifts might not be apparent within a human lifetime? These questions become even more complex when we consider the interconnected nature of ocean systems. Changes in surface waters can affect deep-sea ecosystems in ways we're only beginning to understand. Climate change is altering ocean temperatures, chemistry, and circulation patterns in ways that could have profound effects on deep-sea communities. But predicting these effects requires understanding baseline conditions and natural variability in environments we've barely begun to explore. The deep ocean also holds secrets about the history of life itself that could reshape our understanding of evolution. In the most ancient rocks on Earth, we find evidence that life began in environments very similar to those around modern hydrothermal vents. The chemical conditions, the energy sources, the physical environment of these deep-sea oases might be similar to the conditions where life first emerged billions of years ago. This means that studying modern deep-sea ecosystems might give us insights into the earliest forms of life on Earth. The organisms living around hydrothermal vents today might be the closest living relatives to the first life forms that evolved in Earth's primordial oceans. Their biochemistry, their metabolic pathways, their genetic codes all contain information about the origin of life that we're only beginning to decode. But accessing this information requires techniques and technologies that push the boundaries of what's possible. The conditions around hydrothermal vents are so extreme that most conventional sampling methods simply don't work. The combination of crushing pressure, searing heat, and toxic chemistry destroys most instruments before they can collect meaningful data. Scientists have had to develop entirely new approaches to studying these environments. Specialized submarines that can withstand the conditions around hydrothermal vents. Sampling devices that can collect organisms without exposing them to lethal pressure changes. Laboratory techniques that can maintain deep-sea organisms in conditions similar to their natural habitat. Even with these advances, much of what we know about hydrothermal vent ecosystems comes from brief observations made during expensive and dangerous deep-sea expeditions. A typical research dive to a hydrothermal vent might last only a few hours, during which scientists must accomplish months of planned research objectives under conditions where equipment failure could be catastrophic. The data collected during these brief windows requires years of analysis and interpretation. A single water sample from a hydrothermal vent might contain dozens of previously unknown species of bacteria. A small piece of mineral formation might preserve evidence of chemical processes that have been operating for thousands of years. Each sample represents a tiny piece of a vast puzzle that we're only beginning to assemble. But perhaps the most profound mystery of the deep ocean isn't about the life forms that exist there, or the geological processes that shape the seafloor, or even the role of the ocean in regulating our planet's climate. Perhaps the deepest mystery is about consciousness itself, about the nature of awareness and intelligence in an environment so alien to our own experience. In the crushing darkness of the deep sea, we've discovered forms of intelligence that challenge our understanding of what it means to be aware, to think, to experience the world. Octopuses that live in the deep ocean display problem-solving abilities that rival those of many vertebrates, despite having evolved intelligence independently from the lineage that led to human consciousness. They can use tools, solve complex puzzles, and demonstrate what appears to be individual personality and learning ability. But these deep-sea cephalopods exist in an environment so different from our own that their form of consciousness might be fundamentally alien to human experience. They live in a world without light, where communication happens through touch and chemical signals rather than vision. Their bodies can change color and texture in ways that might represent a form of communication as complex as human language, but operating according to principles we don't understand. Some researchers suggest that the color-changing displays of deep-sea cephalopods might represent a form of visual language, a way of communicating complex information through rapid changes in skin pattern and texture. If this is true, then these creatures might be having conversations that we can observe but not comprehend, exchanging information in a visual vocabulary that evolution has refined over millions of years. The implications are staggering. If intelligence can evolve in the deep ocean, operating according to principles completely different from terrestrial consciousness, what does that tell us about the nature of awareness itself? Could there be forms of intelligence in the deep sea that we wouldn't even recognize as conscious? Communities of organisms that think collectively in ways that transcend individual awareness? These questions push us to the very limits of what science can address. How do you study consciousness in creatures that live under conditions where direct observation is nearly impossible? How do you distinguish between complex behavior and true awareness in organisms whose sensory world is completely alien to human experience? The deep ocean forces us to confront the possibility that intelligence and consciousness might be far more common in the universe than we've assumed, but also far more diverse. If awareness can evolve in the crushing darkness of the abyss, if intelligence can emerge in creatures that experience the world through chemical gradients and pressure waves, rather than light and sound, then the universe might be filled with forms of consciousness that we lack the conceptual framework to recognize or understand. This recognition brings us full circle to the fundamental mystery of the ocean itself. We've spent most of this journey exploring the physical and biological mysteries of the deep sea, the unknown species and geological processes that wait in the darkness. But perhaps the most profound mystery is epistemological, about the limits of human knowledge and the possibility that the ocean contains forms of reality that transcend our ability to comprehend them. The ocean teaches us humility, not just because it's vast and unexplored, but because it demonstrates that existence itself is far more creative and diverse than our land-based perspective has prepared us to imagine. Every expedition into the deep sea returns with discoveries that force us to expand our conception of what's possible, what's real, what forms life and consciousness and intelligence can take. But these discoveries also reveal the limitations of human perspective. We are surface creatures, adapted to understand the world through sight and sound, and the familiar physics of air and solid ground. The ocean operates according to different principles, where pressure replaces gravity as the dominant force, where chemical energy replaces solar energy as the foundation of life, where time moves at a different pace and space has a different structure. Understanding the ocean requires not just new technologies and new scientific methods, but new ways of thinking about reality itself. It requires accepting that our familiar categories of understanding, our surface-dwelling intuitions about how the world works, might be inadequate for comprehending the largest habitat on our own planet. This intellectual humility is perhaps the ocean's greatest gift to human consciousness. In an age when it sometimes seems that science has explained everything, when technology appears to give us mastery over the natural world, the ocean reminds us that mystery is not the enemy of knowledge, but its eternal companion. The more we learn about the deep sea, the more we realize how much we don't know, how much wonder still awaits discovery. The 90% of the ocean that remains unexplored isn't just a scientific challenge or a technological frontier. It's a guarantee that future generations will inherit a world still capable of surprising them, still filled with genuine mystery and wonder. In an era when children grow up with instant access to information about almost everything, the ocean ensures that there will always be real unknowns, authentic mysteries that can't be solved with a quick internet search. This preservation of mystery isn't just important for scientists and explorers. It's essential for the human spirit itself. Wonder is not a childish emotion to be outgrown, but a fundamental aspect of consciousness that connects us to the larger cosmos. The ocean's mysteries remind us that we are part of something vast and strange and beautiful that transcends our understanding. As we drift toward the completion of our journey into these liquid depths, we find ourselves changed by the encounter with such profound mystery. The ocean has taught us that our planet is far stranger and more wonderful than we imagined, that life is more creative and resilient than we dreamed, that consciousness itself might take forms we haven't begun to comprehend. But perhaps most importantly, the ocean has reminded us of our place in the cosmic story. We are not separate from these underwater realms, not outside observers studying a foreign environment. We are part of the same evolutionary process that created the creatures of the deep sea. We carry the ocean within us in the salt of our blood, the calcium of our bones, the water that comprises most of our bodies. The ocean's mysteries are our mysteries because we are ocean creatures ourselves, terrestrial expressions of the same creative force that filled the deep sea with wonders we're only beginning to discover. Understanding the ocean isn't just about mapping unexplored territory or cataloging unknown species. It's about understanding ourselves, our origins, our connection to the vast web of life that connects every drop of water to every living thing. Tonight, as you settle into the rhythm of your own breathing, as you feel the familiar weight of your body supported by solid ground, remember that you are held by the same gravitational forces that shape the ocean's currents, sustained by the same chemical processes that power life in the deepest trenches, connected by the same evolutionary history to every creature that swims in the darkness of the abyss. The ocean's mysteries surround you, flow through you, connect you to wonders that stretch from the smallest bacteria in hydrothermal vent communities to the largest ecosystems spanning entire ocean basins. You are part of this story, this ongoing exploration, this eternal dance between the known and unknown that makes existence itself a source of endless fascination and wonder. And in that recognition, in that sense of connection to mysteries larger than individual understanding, perhaps we find the deepest truth the ocean has to offer. We are not masters of this planet, not separate from its processes, not outside observers of its wonders. We are participants in an ongoing story of discovery and creation that connects us to every depth, every current, every creature that calls the ocean home. The 90% of the ocean that remains unexplored isn't waiting for us to conquer it. It's inviting us to join it, to recognize ourselves as part of the vast community of life that flows through every drop of water, every grain of sand, every breath of air that sustains existence on this remarkable planet we share. In the end, the ocean's greatest mystery might not be what lies hidden in its depths, but what it reveals about the nature of mystery itself. In a universe vast beyond imagination, on a planet filled with wonders that exceed our ability to catalog or comprehend them, we find ourselves blessed with the capacity for wonder, for curiosity, for the kind of awe that transforms simple existence into conscious participation in the ongoing story of the cosmos. The ocean ensures that this story will never end, that wonder will never be exhausted, that mystery will always beckon from just beyond the edge of our understanding. And in that endless invitation to discovery, in that guarantee of perpetual wonder, we find perhaps the most precious gift any environment could offer to conscious beings lucky enough to call it home. As we float deeper into this contemplation of oceanic mysteries, we encounter something that challenges our most fundamental assumptions about the nature of discovery itself. You see, the ocean doesn't reveal its secrets the way we might expect. It doesn't follow the familiar pattern of exploration where maps get filled in, territories get claimed, frontiers get conquered one methodical step at a time. Instead, the ocean operates like a vast, three-dimensional puzzle where each piece we discover only reveals how many more pieces we're missing. Every answer we find opens doors to entire wings of questions we never knew existed. It's as if we're trying to understand a symphony by hearing only scattered notes, attempting to comprehend a vast library by reading random sentences from books written in languages we're still learning to decode. Consider what happened just a few years ago when researchers exploring the deep Pacific discovered what they called the purple sock creature. This isn't a whimsical nickname for some familiar species. It's literally a scientific designation for an organism. So unlike anything we've seen before, that researchers couldn't even determine what major group of animals it belonged to. Was it a type of sea cucumber? A primitive chordate? Something entirely new that didn't fit into any existing category? This single discovery, made during a brief dive to depths that few humans have ever visited, forced scientists to reconsider fundamental questions about animal evolution and the diversity of life on Earth. One small, purple, sock-shaped creature found in the darkness of the abyss opened up entirely new branches on the tree of life, suggesting that our current understanding of how animals are related to each other might be missing huge chapters of the story. But here's what makes this discovery even more remarkable. The purple sock was found in an area of the deep sea that had never been explored before, in waters so remote that reaching them required weeks of travel and millions of dollars in research vessel time. The creature was observed for only a few minutes during a single dive, captured on video under challenging conditions, and then disappeared back into the darkness from which it came. This pattern repeats constantly in deep-sea exploration. We catch glimpses of phenomena that challenge everything we thought we knew. But the glimpses are so brief and the conditions so extreme that we're left with more questions than answers. It's like trying to understand a foreign culture by looking through a keyhole for a few seconds at a time. The ocean's resistance to easy categorization extends beyond just individual species. Entire ecosystems in the deep sea operate according to principles that seem to violate our basic understanding of how life works. We've discovered communities of organisms that exist in a state of suspended animation for years at a time, awakening only when specific chemical conditions trigger their metabolism back into activity. Imagine creatures that can essentially pause their lives, waiting in the darkness for conditions to improve, then resume their biological processes as if no time had passed. This isn't hibernation, as we understand it from terrestrial animals. It's a form of existence that seems to operate outside our normal concepts of life and death, activity and rest, presence and absence. These discoveries force us to expand our definition of what it means to be alive. If organisms can exist in states of suspended animation for years, if they can pause and resume their biological processes at will, if they can survive conditions that would be instantly lethal to most other life forms, then life itself is far more flexible and creative than we ever imagined. But studying these phenomena presents challenges that go far beyond the technical difficulties of deep-sea exploration. How do you observe creatures that might be active for only a few days out of every year? How do you study ecosystems that operate on timescales that exceed the duration of any research grant or human career? The temporal dimension of ocean mysteries becomes even more complex when we consider the role of deep currents in shaping global climate patterns. The water flowing through the deepest parts of the ocean began its journey at the surface decades or centuries ago, carrying with it chemical signatures and temperature records from a time before human civilization began keeping systematic records of ocean conditions. These deep currents are like rivers of memory flowing through the ocean's depths, carrying information about past climate conditions, past ice ages, past periods of warming and cooling that shaped the evolution of life on Earth. But reading these liquid archives requires understanding processes that operate over timescales that dwarf human observation. A single molecule of water might spend 1,000 years circulating through the deep ocean before returning to the surface. During that millennium-long journey, it travels pathways that connect every ocean basin, carrying nutrients from one hemisphere to another, transporting heat from the tropics to the poles, participating in chemical cycles that regulate the composition of the atmosphere itself. But we've only recently developed the technology to trace these pathways, to understand how deep ocean circulation connects to surface climate patterns, to predict how changes in one part of the ocean might affect conditions thousands of miles away and decades into the future. We're like detectives trying to solve a crime where the evidence is scattered across the globe and the timeline spans centuries. The ocean's role as a climate regulator becomes even more mysterious when we consider the biological processes happening in its depths. The creatures living in the deep sea aren't just passive passengers in the ocean's circulation system. They're active participants, consuming nutrients, producing waste, migrating vertically through the water column in patterns that affect the distribution of carbon, nitrogen, and other essential elements. Every night, billions of small organisms rise from the depths toward the surface to feed, then descend again before dawn. This daily vertical migration, involving more biomass than any terrestrial migration, creates a biological pump that transports nutrients and carbon between different layers of the ocean. But we understand almost nothing about how this process works, how it's regulated, or how it might be affected by changing ocean conditions. The creatures participating in this migration range from tiny zooplankton barely visible to the naked eye to squid the size of school buses. They travel distances that would be equivalent to a human walking from New York to Philadelphia every single day. But they do it through water under crushing pressure, in complete darkness, guided by instincts and navigation systems we don't understand. Some of these migrating organisms can produce their own light, creating bioluminescent displays that turn the ocean into a liquid aurora. Others navigate using magnetic fields, chemical gradients, or pressure changes so subtle that our most sensitive instruments can barely detect them. Still others seem to coordinate their movements across vast distances, participating in synchronized behaviors that span entire ocean basins. But observing this daily migration requires technology that can operate in the deep ocean for extended periods, tracking individual organisms or populations through their vertical journeys without disturbing their natural behavior. It's like trying to study the migration patterns of birds while blindfolded, using only sound and touch to understand movements that span thousands of meters of vertical space. The acoustic dimension of the ocean adds another layer of mystery to these deep-sea phenomena. The ocean isn't silent. It's filled with sounds produced by geological processes, by the movement of water masses, and by the creatures that inhabit its depths. But these sounds travel through water in ways that create acoustic environments, unlike anything in the terrestrial world. Low-frequency sounds can travel for thousands of miles through the ocean's sound channel, a layer of water where acoustic signals can propagate with minimal energy loss. Whales have long been known to use this acoustic highway for long-distance communication, but we're discovering that many other deep-sea creatures also produce sounds that can travel vast distances through the ocean's depths. Some of these acoustic signals might be used for navigation, allowing creatures to create mental maps of underwater terrain by listening to the echoes of their own calls. Others might be used for communication between individuals separated by hundreds or thousands of miles. Still others might serve purposes we haven't even imagined, creating acoustic landscapes that exist entirely outside human perception. But human activities are adding new sources of noise to the ocean's acoustic environment. Shipping traffic, offshore construction, military sonar systems, and industrial activities all contribute sounds that can mask natural acoustic signals or disrupt communication systems that marine organisms have relied on for millions of years. The problem is that we understand so little about natural ocean acoustics that we can barely assess the impact of these human-generated sounds. We're adding noise to a conversation we can't understand, potentially disrupting communication systems we don't even know exist. The chemical dimension of ocean mysteries presents equally profound challenges to human understanding. The ocean isn't just water. It's a complex solution containing dissolved minerals, gases, organic compounds, and biological molecules that create chemical gradients and reactions throughout the water column. Some deep-sea organisms can detect chemical changes so subtle that they're measuring concentrations of molecules that would be undetectable to most analytical instruments. They use these chemical signals to navigate, to find food, to locate mates, to avoid predators. They live in a world of invisible chemical trails and gradients that create a landscape as complex and detailed as any visual environment. But studying these chemical processes requires sampling techniques that don't disturb the very gradients and concentrations we're trying to measure. It's like trying to study the smell of a flower while wearing a gas mask, or attempting to understand the taste of wine while suffering from a severe cold. The ocean's chemical environment is also constantly changing in response to geological processes, biological activity, and increasingly human influences. The carbon dioxide we're adding to the atmosphere isn't just changing the chemistry of surface waters, it's creating cascading changes throughout the entire ocean system, altering pH levels, affecting the ability of organisms to build shells and skeletons, changing the solubility of minerals and the availability of nutrients. These chemical changes are happening faster than at any time in the last 50 million years, creating conditions that most marine organisms have never encountered in their evolutionary history. But predicting how ocean ecosystems will respond requires understanding baseline chemical conditions and natural variability in environments we've barely begun to explore. The challenge becomes even more complex when we consider the interconnected nature of ocean chemistry, biology, and geology. Changes in one part of the system can trigger cascading effects that ripple through the entire ocean, but these effects might not become apparent for decades or centuries. We're conducting a global experiment on ocean chemistry without understanding the systems we're changing. It's like adjusting the ingredients in a recipe without knowing what we're trying to cook, or how the different components interact, or what the final result is supposed to taste like. The ocean's response to these changes will likely involve processes and organisms we haven't discovered yet, operating through mechanisms we don't understand, over timescales that exceed our ability to observe directly. We're trying to predict the future of a system whose present we barely comprehend. But perhaps the most humbling aspect of the ocean's chemical mysteries is what they reveal about the fundamental interconnectedness of life on Earth. The oxygen you're breathing right now was partially produced by marine photosynthesis. The calcium in your bones came from ancient marine organisms. The salt in your blood echoes the chemistry of primordial seas. You are not separate from the ocean's chemical systems. You are part of them. Every breath you take, every meal you eat, every glass of water you drink connects you to chemical cycles that span the globe and stretch back billions of years. The ocean's chemistry isn't just something happening out there in the deep sea. It's happening inside you, right now, as your body maintains the delicate chemical balance that keeps you alive. This recognition transforms our relationship with ocean mysteries from academic curiosity to personal necessity. Understanding the ocean isn't just about satisfying scientific interest or protecting marine ecosystems. It's about understanding the chemical foundation of our own existence, the planetary life support systems that make human civilization possible. But accessing this understanding requires a fundamental shift in how we think about time, space, and causality. The ocean operates on scales that challenge human intuition. Processes that seem slow and gradual from our perspective might be rapid and dramatic from the ocean's perspective. Changes that seem local and limited might have global consequences that won't become apparent for generations. The ocean teaches us that the Earth is not a collection of separate systems that we can study in isolation. It's an integrated whole where changes in one component affect everything else, where the deep sea is connected to surface waters, where marine chemistry affects terrestrial climate, where the health of ocean ecosystems determines the future of human civilization. As we drift deeper into contemplation of these interconnected mysteries, we begin to understand that the ocean's secrets aren't just about what's hidden in its depths. They're about the nature of complexity itself, about how simple physical and chemical processes can give rise to systems of stunning beauty and sophistication. The ocean is a masterclass in emergence, the process by which simple components combine to create properties and behaviors that are far more complex than the sum of their parts. Individual water molecules, following basic physical laws, create currents that shape global climate. Simple chemical reactions, repeated billions of times, create the conditions for life. Basic biological processes, operating over millions of years, create ecosystems of breathtaking diversity and resilience. But understanding emergence requires a kind of thinking that doesn't come naturally to human minds. We're pattern-seeking creatures, evolved to understand cause and effect relationships that operate on timescales we can observe directly. The ocean's emergent properties unfold over periods that span thousands of human lifetimes, through processes so complex that they challenge our most sophisticated mathematical models. This is why the ocean remains mysterious despite centuries of scientific study. We're not just dealing with unknown facts or undiscovered species, we're grappling with forms of complexity that push the boundaries of human comprehension, systems whose behavior emerges from interactions too numerous and too subtle for any mind to track completely. The ocean humbles us not just because it's vast and unexplored, but because it demonstrates that reality itself is far more intricate and surprising than our everyday experience prepares us to understand. Every wave that breaks on every shore is the product of forces and processes that connect it to weather patterns, ocean currents, tidal cycles, and geological processes operating across multiple timescales and spatial scales. Even the simplest aspects of ocean behavior emerge from complexity that exceeds human ability to fully comprehend. A single drop of seawater contains more individual molecules than there are stars in the observable universe. Each molecule is engaged in constant motion and interaction with its neighbors, creating the fluid properties that allow oceans to exist at all. The ocean's mysteries aren't just about what we haven't discovered yet. They're about the fundamental limits of what any finite intelligence can understand about complex systems. Even if we could somehow observe every part of the ocean simultaneously, even if we could track every molecule and every organism and every current, the emergent properties of the system would still surprise us. This recognition brings us to perhaps the most profound insight the ocean offers about the nature of knowledge itself. Mystery isn't the enemy of understanding. It's the natural companion of complexity. The more we learn about any sufficiently complex system, the more we realize how much we don't know. How many new questions emerge from every answer we find. The ocean ensures that human knowledge will always have frontiers, that science will always have new territories to explore, that wonder will always be justified by genuine unknowns waiting to be discovered. In an age when it sometimes seems that technology has made the world smaller and more predictable, the ocean guarantees that mystery and exploration will remain part of the human experience. This guarantee isn't just important for scientists and researchers, it's essential for the human spirit itself. We are creatures who need mystery, who thrive on the challenge of the unknown, who find meaning in the pursuit of understanding even when complete understanding remains forever beyond our reach. The ocean provides that challenge on a scale that matches our highest aspirations. It offers mysteries deep enough to occupy human curiosity for centuries to come, complex enough to require our most creative thinking, beautiful enough to inspire our highest reverence for the natural world. As we near the completion of our journey into these liquid depths, we find ourselves changed by the encounter with such profound mystery. The ocean has revealed itself not just as a body of water covering most of our planet, but as a teacher of humility, a source of wonder, a reminder that we live in a universe far stranger and more magnificent than our daily experience suggests. The 90% of the ocean that remains unexplored isn't just a scientific challenge or a technological frontier. It's a guarantee that future generations will inherit a world still capable of surprising them, still filled with genuine mystery and authentic wonder that can't be reduced to data points or explained away by simple theories. Tonight, as you settle into the familiar rhythms of your own breathing, as you feel the steady beat of your heart pumping blood, that carries the chemical signature of ancient seas, remember that you are connected to these oceanic mysteries in ways both profound and immediate. The water cycle that sustains all terrestrial life begins and ends in the ocean. The climate patterns that shape your daily experience are regulated by currents and chemical processes operating in depths no human has ever seen. You are not an outside observer of these ocean mysteries. You are a participant in them, a temporary arrangement of matter and energy that emerged from the same evolutionary processes that filled the deep sea with wonders we're only beginning to discover. Your existence is proof that the ocean's creativity extends far beyond the boundaries of marine ecosystems, that the same forces that create bioluminescent displays in the abyss can also create conscious minds capable of contemplating their own origins. The ocean's mysteries are your mysteries because you are made of the same elements, governed by the same physical laws, part of the same planetary story that connects every drop of water to every living thing. Understanding the ocean isn't separate from understanding yourself. It's part of the same quest to comprehend the extraordinary complexity and beauty of existence itself. And in that recognition, in that sense of connection to mysteries larger than individual understanding, we find perhaps the deepest truth the ocean has to offer. We are not masters of this planet, not separate from its processes, not outside observers of its wonders. We are expressions of the same creative force that fills the ocean with creatures we've never seen, processes we don't understand, and possibilities we can't imagine. The 90% of the ocean that remains unexplored isn't waiting for us to conquer it. It's inviting us to join the ongoing story of discovery and creation that connects every depth to every surface, every current to every coast, every mystery to every moment of wonder that makes existence itself a source of endless fascination. As we drift toward the completion of our journey through these liquid mysteries, we encounter perhaps the most profound realization of all. The ocean's greatest secret isn't hidden in its deepest trenches or its most remote corners. It's hidden in plain sight, flowing through every current, suspended in every drop of seawater, encoded in the very rhythm of the tides themselves. The ocean is alive in ways we're only beginning to comprehend. Not just teeming with life, but alive as a system, breathing with the slow pulse of thermohaline circulation, thinking with the distributed intelligence of countless interconnected processes, remembering through the chemical signatures preserved in its depths. It's a planetary consciousness operating on scales so vast that we can barely perceive its thoughts, so ancient that its memories stretch back to the birth of our world. Consider this extraordinary fact. The ocean doesn't just contain water. It is water in its most sophisticated form, organized into patterns of stunning complexity and beauty. Every molecule participates in cycles that connect the smallest droplet to the grandest currents, the briefest wave to the most enduring circulation patterns. The ocean is water that has learned to dance, to sing, to create, to preserve and share the story of our planet across billions of years. But perhaps most remarkably, the ocean has learned to dream. In its deepest places, where pressure and darkness create conditions unlike anywhere else in the known universe, the ocean dreams up forms of life so extraordinary they seem like science fiction. Creatures that glow with their own light in the eternal darkness, organisms that build cities of living glass, communities that thrive on the chemical energy of the Earth's molten heart. These aren't just biological curiosities, they're expressions of the ocean's imagination, proof that given enough time and space, water can become anything. The ocean doesn't just support life, it invents life, constantly experimenting with new forms, new possibilities, new ways of being that expand the very definition of what existence can become. And we are part of this great experiment. Every human being carries the ocean within them, not just in the salt of their blood or the water of their cells, but in the very structure of their consciousness. The electrical patterns that create our thoughts flow through neural networks bathed in fluid environments that echo the chemistry of ancient seas. Our brains are essentially sophisticated arrangements of seawater, organized into patterns complex enough to contemplate their own oceanic origins. The ocean's mysteries aren't separate from us. They flow through us, think through us, wonder about themselves through the curious minds they helped create. When we stand at the edge of the sea and feel drawn to its depths, when we're mesmerized by the rhythm of waves or the play of light on water, we're experiencing recognition. The ocean recognizing itself through eyes it helped evolve. Consciousness greeting consciousness across the boundaries of scale and time. This recognition transforms our relationship with the 90% of the ocean that remains unexplored. We're not just studying an external environment, we're participating in a conversation between different aspects of the same planetary intelligence. Every scientific expedition into the deep sea is the ocean investigating itself, using human curiosity as one of many tools for self-discovery. The technologies we develop to explore the depths, the questions we ask about marine ecosystems, the wonder we feel when we encounter something unexpected in the abyss, all of these are expressions of the ocean's own drive to understand itself. We are the ocean becoming curious about its own depths, developing the capability to visit its most remote corners, to illuminate its darkest places, to bring the secrets of the deep into the light of conscious understanding. But this process of oceanic self-discovery is just beginning. The 90% that remains unexplored represents not just unknown territory, but unknown possibilities for what the ocean might become. As climate change and human activity alter marine environments, as new species evolve and existing ecosystems adapt, the ocean continues to reinvent itself in ways we can't predict or control. The deep sea isn't a museum of ancient wonders preserved in eternal darkness. It's a laboratory where the future is being written in currents and chemistry, in the endless adaptation of life to changing conditions. Every expedition into the abyss doesn't just discover what already exists, it witnesses the ocean in the process of becoming something new. The creatures we find in the deepest trenches, the ecosystems thriving around hydrothermal vents, the vast communities of organisms migrating through the water column every night, all represent the ocean's ongoing creativity. They're not just biological phenomena, they're expressions of planetary intelligence, proof that given enough time and space, and the freedom to experiment, consciousness can emerge in forms we're only beginning to imagine. This perspective transforms the urgency of ocean exploration from a scientific imperative to something far more profound. We're not just trying to catalogue species or map seafloor topography. We're participating in the ocean's attempt to understand itself before climate change and human activity alter it beyond recognition. We're racing to document a form of planetary consciousness before it transforms into something entirely different. The window of opportunity for this understanding is closing more rapidly than we might wish. Every year, ocean acidification changes marine chemistry in ways that affect the deepest ecosystems. Rising temperatures alter circulation patterns that have remained stable for thousands of years. Human activities introduce new sounds, new chemicals, new forms of disturbance into environments that evolved in isolation over millions of years. We're witnessing the ocean in transition, changing from one state of being to another at a pace that exceeds the rate of our exploration. The mysteries we discover today might not exist tomorrow. The ecosystems we're just learning to understand might transform or disappear before we can fully comprehend their significance. This temporal urgency adds poignancy to every deep-sea discovery, every new species documented, every ecosystem mapped. We're not just explorers documenting unknown territory. We're witnesses to a planetary transformation, recording the final chapters of one oceanic era before the next begins. But this transformation also offers hope. The ocean's creativity hasn't been exhausted by 4 billion years of evolution. Its capacity for innovation, for adaptation, for generating new forms of beauty and complexity continues to operate even under changing conditions. The ocean that emerges from our current period of rapid change might be different from the one we're trying to understand today, but it will likely be no less magnificent, no less mysterious, no less capable of inspiring wonder and humility. The ocean teaches us that change isn't the enemy of mystery, it's mystery's greatest ally. Every transformation creates new unknowns, new possibilities, new frontiers for exploration and understanding. Even if we could somehow explore every cubic meter of today's ocean, tomorrow's ocean would present entirely new mysteries as species adapt, ecosystems evolve, and planetary systems continue their eternal dance of creation and transformation. This guarantee of perpetual mystery offers perhaps the most profound gift any environment could provide to conscious beings. In a universe where entropy suggests that everything tends towards simplicity and uniformity, the ocean demonstrates that complexity and beauty can persist, can grow, can continue to surprise us across scales of time that dwarf human civilization. The 90% of the ocean that remains unexplored represents more than unknown territory. It represents the guarantee that wonder will never be exhausted, that curiosity will always be rewarded, that the universe will continue to offer challenges worthy of our highest aspirations and deepest reverence. As you settle into the final moments of this liquid meditation, as you feel the familiar weight of your body supported by solid ground, while your mind drifts through imagined depths, remember that you carry within you the same creative force that fills the ocean with wonders we've barely begun to discover. You are water that has learned to think, consciousness that emerged from the same planetary processes that create bioluminescent symphonies in the abyss. The ocean's mysteries are your inheritance and your responsibility. They remind you that you live on a planet still capable of surprising you, still filled with authentic unknowns that no amount of technology or information can fully resolve. They invite you to remain curious, to stay humble before the vast complexity of existence, to find wonder not just in distant discoveries, but in the extraordinary fact of your own awareness. Tonight, as you drift between waking and sleeping, between the familiar world of air and the mysterious realm of water, let yourself float in the recognition that mystery isn't something to be solved, but something to be celebrated. The ocean's depths will continue to hide their secrets long after you and I have returned to the elements from which we came. But in this moment, in this brief flowering of consciousness from cosmic dust and ancient seawater, you have the extraordinary privilege of wondering about wonders that stretch from the smallest bacterial communities to the vastest current systems that shape our world. The ocean doesn't just cover 90% of our planet's surface, it covers 90% of possibility itself, ensuring that no matter how much we learn, how far we explore, how sophisticated our understanding becomes, there will always be more mystery waiting just beyond the reach of our deepest submersibles, our most sensitive instruments, our most creative theories. And in that endless invitation to discovery, in that guarantee of perpetual wonder, we find the ocean's greatest gift to consciousness itself. We are the universe becoming curious about its own depths, water contemplating water, mystery recognizing mystery, across the vast expanse of space and time that connects every drop to every ocean, every question to every answer, every moment of wonder to the infinite possibility that surrounds us like the deepest, most welcoming sea. The mysteries of the ocean ensure that wonder will never die, that exploration will never end, that the conversation between consciousness and cosmos will continue for as long as there are minds to ask questions and depths to explore. And in that conversation, in that eternal dance between the known and unknown, we find our place not as conquerors of mystery, but as partners in the ongoing story of discovery that makes existence itself a source of endless fascination and joy. Sweet dreams, fellow explorer of the vast unknown. The ocean's mysteries will be waiting when you wake, ready to inspire new questions, new adventures, new moments of awe at the extraordinary complexity and beauty of the world we're privileged to call home.